Yeah, hello to everyone who are attending today's Weight and Biases Salon. I would start by thanking Charles for inviting me to the salon today. In today's talk, I'll be basically discussing about the work with my fantastic collaborator, Sarah Hooker from Google, about estimating example difficulties using variance of gradients. So I guess most before going to the depth of the work, I would like to just provide some basic motivations for studying the relative importance between different samples during the training process. So understanding individual samples importance is very important, given that modern data sets are large, with sometimes data sets like ImageNet, they comprise of more than million of images. So this is not feasible for an individual to look at individual explanations of each data point in these huge data sets. Moreover, it is also critical to understand the relative importance of individual classes and inspect images that the model finds easier or more challenging. Uh, Last but not the least, most of the current works in artificial intelligence, XAI, are focused on explaining model behavior on single or a group of explanations. However, these don't actually highlight the inherent bias of the model towards features like, say, colors or textures in an image classifier model. So these were like the motivations that prompted us to move into this direction and explore the variance of gradients. So with respect to explanations, most of the earliest work in XAI was based on model gradients. Now, using vanilla gradients is intuitive as they have a very clear connection to the neural network function. Basically, we have an image, let's say. We can easily calculate its vanilla gradient by backpropagating the loss with respect to the input image and get these gradient representations of the model. However, following works showed that gradients are very noisy and hence uninterpretable. This led to several works which tried to improve the gradient maps by either smoothing them or using methods like guided backpropagation or trying to integrate the gradients between a baseline image, let's say a gray image, and the input image, here the image of the dog. As one would observe in all these different gradient maps, what most researchers were trying to do was to tune these gradients so to give them some interpretability with context to the raw vanilla gradients so that these maps can be understandable to end users like us, humans. However, one may also question that the gradients can be the best explanation of a model because that is what the model uses to learn the given objective function, right? So this actually brings us to why variance of gradients. And as I said before, the raw input vanilla gradients can be the best explanations of a model in some context. So we hypothesize that gradients of examples that can be easily learned by the model will converge quickly during the early training of the whole model, as compared to the challenging examples where the gradients could not converge quickly. So following this hypothesis, what we basically do is we calculate a proxy metric that's like the variance of gradients for quantifying the relative importance between individual samples of the training and the testing data sets. In this figure, we basically show an input image that's the image of the bird, and we show its gradients as it is evolving during different checkpoints the whole training process. This image was taken from the ImageNet dataset, and hence it was trained using a ResNet 50 architecture for 90 epochs. So we can easily calculate the gradients with respect to any particular checkpoint throughout the training process. And that's like one of the best USP of using VOG score. So using these gradients, we come up with this VOG scalar score. In the given equation, the STI basically represents the gradients of the particular image at the given checkpoint t. Mu I is basically the mean gradients of a given number of checkpoints. Here, since k determines the number of checkpoints across which we are trying to calculate the gradients, and n determines the number of number of pixels in the whole images. So in a way, we can actually interpret the VOG score as a scalar score which represents the VOG across each pixel of the image. And then we basically take the mean across the whole VOG across all pixels to get just one scalar score for a given input image. So what we do then is calculate these VOG scores for all the training and the testing images in the dataset by using the different checkpoints of the model. So many existing works have shown that there exists different stages of training during a deep neural network. So what we show here is on analyzing the images using the VOG score, we see that images having a low VOG scores are very different than the images which are having high VOG scores. In this particular figure, we trained the ResNet 18 model on CFAR100 dataset, and we tried to visualize the relative importance between the apple class images. Clearly, we see that there's a big cluster of red apples which have a low VOG score as compared to the high VOG score apple images, which are more cluttered. And in some of the images, there are like multiple apples. On comparing this to the late stage training, we see similar patterns where the low VOG score images are more object-centric and have clear view of the object in interest, that is apples, whereas the high VOG samples are more cluttered and they are taken from different vantage points. So one quick question that would come to any model developer or end user is, can we use VOGs to have a relative ranking across each classes? So in this particular experiment, we divided the training process into two stages, which is the early stage and the late stage, comprising of 3 checkpoints. The proposed VOG score then actually discriminates images with clean and cluttered backgrounds, and higher VOG scores images are usually images with zoomed in view, or they are more atypical as compared to low VOG scores. In this particular image, we trained a ResNet 50 architecture on ImageNet dataset, and we basically visualized the cluster of images belonging to the MagPie class. Very surprisingly, we see the same pattern as in the CFAR datasets, where we see the low VOG samples are much more cleaner and have the birds center to the images as compared to the high VOG scores, where you'll see zoomed in views of the bird or cropped images, which are basically the data augmented portions of the datasets. We saw the same pattern for a different class, which is the pop bottle in this case, where the low VOG scores had images comprising of multiple bottles in the same image, whereas the high VOG score had pop bottle images where, let's say, a human was involved, or they were taken from the top view, and all the different styles of pop bottle images. So these qualitative insights gave us a good motivation that VOG can be actually used to understand the different clusters of images during different training process, different training stages, and for different classes too. So moving on to some quantitative results, here we show that VOG can discriminate easy and challenging examples easily. We trained CFAR10 models, and it achieved a testing accuracy of 89.55%. It is to be noted that all the models that I'll be showing now were trained with 100% accuracy. That is, there is some sense of overfitting across all these networks. So we clearly see that the misclassification rate is the highest for the VOG scores, which for the samples which have the high VOG scores. Interestingly, we found the similar patterns across 2 more data sets of CFAR100 and ImageNet. Here, if we see carefully, then the testing accuracies of the CFAR100 and ImageNet datasets were much lower. Hence, that means they were more overfitted. And as compared to CFAR10, that is why we see a much more linear pattern between the VOG scores and the misclassification error rate, where we see a consistent trend that as the VOG scores increases, the misclassification error increases. So these are all good because we can easily use VOGs to understand the testing data sets. But now moving back to the training data sets, then we ask the question that can actually VOG give us more insights about the behavior of the model during different stages. So we took the ImageNet trained ResNet 50 model, and we saw that the behavior completely flips in the early and the late stage. Now, the correlation pattern with accuracy reverses as we see from the early to late stage training, which gives us an interesting viewpoint into the training dynamics of the model. That is basically that early on, the gradient updates have high variance for the easy examples, but once they are being trained, their VOG scores decreases, and later on during the late stage process, the gradient variance is high for only those samples that the model finds challenging. So these were more like looking into a trained model, be it the training data sets or the testing data set. But an interesting application that we thought VOG can be used to is that it can act like an unsupervised auditing tool. Now, it is to be noted that all the results that we have seen until now, the gradients were actually taken using the ground truth class of the particular image. But in real world setting, we often do not know the ground truth class. So the question comes that can VOG serve as a good auditing tool if we don't know the predicted class, or if we don't know the ground truth class of the respective inputs? So what we did here was we took the backpropagated gradient with the top one predicted class of any image, and then we tried to visualize the low VOG and the high VOG samples. To our surprise, we actually see the similar patterns as we saw for the ground truth VOG scores, where we see that images that were correctly predicted by the model were more object-centric as compared to the high VOG samples, where we see blurred out images or images where the object was too much zoomed in. And hence, I mean, that gave us a good indicator that VOG can actually serve as an unsupervised tool, since we do not use any ground truth information of the respective images. Now, all these results are fine, but to build trust with any end user, or even if you're giving a model developer this VOG proxy metric to analyze the model, a key desirable property for any tool would be the consistency. That is basically that we would expect a consistent method to produce a ranking with a very closely bounded distribution of scores across independent runs. To measure the VOG stability, we train 5 networks, 5 ResNet 18 models on CIFAR 10, and then we try to visualize the VOG scores across each of these 5 different trained models. All the 5 models were randomly initialized, so we can expect some variance. But when we visualize the VOG scores with respect to the error performance of these 5 models, we saw more or less like all the VOG scores had the same patterns across the whole across the 5 models, which talks about like the stability of the VOG metric. So these were like basically all the results that I could have summed up today for this talk. So the final takeaways for this VOG paper was that it can serve as an interpretability tool for ranking both training and the testing samples. An interesting advantage of VOG is that it does not need any modification of the architecture, since we always train models and we always capture snapshots during the training process. So it doesn't come with any external additional costs. We can easily just take snapshots of a trained model and then calculate the VOGs of the input images in this case. And the third takeaway would be that the VOG scores can actually aid us in clustering images with respect to each class across the training data sets and the testing data sets, so that we can actually understand the behavior of the model and also know about the dataset bias, whether for say it consists of images of just one unique nature, or it can have a good diversity across in each image class. I think those are like the final takeaways of our work. And yep, you can find our paper on arXiv, and yep, I'm open to questions now.
Great. Thanks, Chirag, for that nice overview of your work. So I have a lot of questions. I encourage folks on Zoom and on YouTube to also chime in if they've got questions of their own. So either in the Q&A on Zoom or in the live chat. on YouTube.
Mhm.
So I guess just to start us off here,
Right.
so how many samples from a class do you need in order to do this variance of gradient operation?
So that's an interesting question, Charles. So thing is, we actually experimented with different checkpoints, but we actually found out that as low as just 3 checkpoints from a model can actually serve, uh, can lead to a good VOG approximation of the whole data set. And in all these results that I presented today, we just took 3 snapshots of the model. Like by that, I mean that during the early stage, we just took 3 snapshots when the model reached decent accuracy for the testing model, for the training data set. And then we, let's say, took the last 3 checkpoints during the end cycle of the training process. So yeah, we just used 3.
I see. And can you clarify? So if I have a single example, I'm going to have, I'm going to have a variety of like gradient values if I backpropagate all the way to the pixel level input.
Right.
Right.
Right. Right.
But that variance isn't what you need. What you need is variance of the gradient over time through training.
Exactly. So what you just described would give us like the gradient for each snapshot. So that would be like basically the gradient heat map of that image at that particular snapshot. But what we are trying to do here is we're trying to calculate the variance of those heat maps, gradient heat maps in this case, across all the different checkpoints, and then calculate the variance.
I see. And one set of questions I really wanted to kind of dive in a little bit is what you can do with this variance of gradient just on the basis of like without doing any training, actually. So like at the very beginning, I haven't done anything with my data set. I have a random network.
Right.
Like, would you be able to look at the variance of the gradient like across random initializations to get a sense for something like this metric? Or is it really important that it's the same network, the same architecture over time?
Right. So if I understand the question correctly, are you asking whether VOG can serve as a prior information before the actual training starts?
Yeah, that's the general direction I'm pushing. And the first idea I had in that direction was just like, let's try 5 different random initializations and do VOG across that.
That's a good question. So we did try this thing up, but actually you actually presented a good point here. So what you're basically saying is in the stability experiment, we trained 5 different models. What you're basically suggesting is we don't train them, we just initialize them and calculate the VOG for the uninitialized model. But then my question would be, if you're not training, then how would you calculate the variance? What you will be basically getting is the gradients for each of those random initializations. Then we can always do the variance across all the 5 different initializations. That is something we can do. But then again, if we do that, then that would not be pertaining to one particular model. That would be like the variance across 5 different runs. Right? So
yeah, I guess the intuition that I kind of have here is, I guess, yeah, the idea is that the example sort of maybe jumping across a decision boundary or something like that, right?
So,
and I suppose, yeah, for different random initializations, maybe you would expect there to be a lot of jumping across decision boundaries, which you wouldn't expect for the same network over time.
That's true. And moreover, for a randomly initialized models, it would be very interesting to see the gradients for each of the inputs, whether all of them will be random or there will be some. So like many works have also showed that even randomly initialized models can serve as good features for the, like there was a paper on deep image prior. So they also show that randomly initialized networks also have some certain characteristic. So in that essence, I guess it's interesting to do this experiment, right?
Relatedly, I think people have found that random networks, if you look at the gradient maps for random networks, those like the things that you presented at the beginning, either the raw gradient maps or something like smooth grad or integrated gradients, you do see a lot of structure even with a randomly initialized network when you do that.
We do some, but the images that I showed earlier were for trained models.
Yeah. This is something so I worked on interpretability for a little bit, and one of the things that was important in our application was we wanted to demonstrate that like it was different from a random network. And I found at least some people reporting that there was much higher overlap than you would expect by chance. It's not the case that the that the gradient map looks random. It sort of concentrates on things like the center of the image and the highest contrast regions of the image.
Right. Yeah, that's a good point. And I think, yeah, that would be interesting to see whether those things actually carry forward to all the images in the particular class. That would be interesting.
What possibilities are there for applying this in, just to start off, like a regression problem based off of computer vision, like a bounding box thing? Like obviously you no longer have the class to like organize things by, but would you be able to detect maybe more difficult examples or something like that?
That's a good question, actually. So we haven't looked into it right now, but I clearly see that we can easily use the same formulation here. But in that case, basically we backpropagate the gradients, not with respect to the ground truth class, but here, as you're saying, we have, like, let's say, the bounding box coordinates. So we can easily backpropagate the loss using the difference in the coordinates, or using the ground truth bounding box or the predicted bounding box. So I think in that sense, it can be used for object detection or image segmentation, those all kind of those different tasks.
Gotcha. And what about in application to different domains where there is also a class, like say like audio classification or sentiment analysis and NLP, something like that?
Yep, I think that's I don't want to sound very philosophical, but I think that's the beauty of VOG in this case, that it does not take anything from the model or the architecture. It just uses the gradients. So in any application or domain, as you're mentioning, if we can by any chance calculate the backpropagated gradients, which is the main point in all deep networks, that we use the backpropagated gradients. So any application doing that can be easily use VOG as a proxy metric.
So I guess the question I have is, do you have any indications that it'll work just as well in one of these other domains? Because, it's not guaranteed that necessarily something, maybe it's very important that there's, say, these max pooling operations that you find in convolutional networks to make this work really nicely or something like that.
So I myself haven't tried this other applications, but we have received some emails regarding interested researchers applying it to sequencing data or segmentation models. So yeah, people are using it as for different applications.
That's exciting. I think, yeah, the emphasis, I think, was in your talk was on a lot of the the data set cleaning kind of side of things, or the outlier detection kind of side of things. Can you talk a little bit more about how you think variance of gradient could be used for the like explainable AI side of things?
So that's a good point. So in this case, you're right. Most of our results were actually focused on detecting out of distribution data or atypical examples during the training process. With respect to explainability, so the gradient maps are itself, as I said, like in 2013, when the work started, people actually felt that gradients can be the best explanation to a model, which some people still believe that, because it has a clear connection to the model, right? So in that case, we're actually using some notions of explainability in this case. Now, the other point that you brought up is, can we use, rather than using just raw gradient maps, can we actually use these different variants of gradients, like the smooth grad or integrated gradients, and then calculate the VOGs on those XAI-based heat maps algorithms? So that would be something interesting to try.
I see. Yeah. So the idea is it's like a variance of the map over time, and that doesn't have to be the gradient. It could be any other map.
Exactly. So exactly. That's the point. So right now we are just taking the vanilla gradients, but we can always try to extrapolate other gradient-based methods on this.
That's interesting. So I guess in the last couple minutes of your time, could you talk a little bit about sort of the future directions you see you taking this work, and maybe your career in ML?
So I'll try to make it brief. So with respect to VOG, I think there are a few interesting directions. Some of them, as we discussed, that can be actually use VOGs, the results that we have for our image classifier, and then use it for different applications and other domains also, not respect to just images, but let's say language models and graph networks. And that's like one very promising direction. And other one is also to use the VOG scores and understand the training on the fly and basically leverage the VOG scores to improve the training performance of a model. So that would be interesting direction.
Yeah, that does seem, yeah, there's a lot of room still, I think, to improve what people do during training for things, out of distribution data is a hard, it's not something you're just going to resolve with normal gradient descent. So that sounds like a great direction to take things.
Right, exactly.
All right. Well, thanks for coming on, Chirag, and thanks for presenting and thanks for doing some really great and interesting research and being willing to present it to us.
Thank you, Charles, for inviting me today. It was a pleasure talking to you.